Hello everyone, this is the 14.5 video. It's chain rule for multivariable functions, so very useful. I think it's kind of a short section, so we'll see, I guess, at the end how long this is in comparison to the other videos. So this is going to be a fairly simple extension of the chain rule for functions of a single variable. So we're starting out with a theorem that lets us do this, and we're going to discuss the theorem. And this is for a function of two variables, but it's the same for functions of any number of variables. Okay. All right, so suppose f of xy is differentiable function of x and y, where x equals g of t and y equals h of t. Okay, so f is a function of x and y, and then those x and y's are themselves functions of some other variable t. And we're saying such that g and h are differentiable. Okay, so notice the two definitions of differentiable here. This is our definition of differentiable for multivariable functions, which we talked about in the last video. And then this, since g and h are just functions of a single variable, this is our usual idea of differentiable for single variable functions. All right, so if f is differentiable and x and y are differentiable, then fxy, this whole thing, is going to be a differentiable function of t. Okay, so now we're saying, okay, we can differentiate this in terms of x and y, and we can differentiate these in terms of t. Well, that means we can differentiate this thing in terms of t. And that derivative, df dt, is going to be partial of f with respect to x times derivative of x with respect to t plus partial of f with respect to y times derivative of y with respect to t. So let's just translate this for a second. Okay, so we have this function fxy, and then x equals g of t, h equals y equals h of t. And we are trying to find, we're asking ourselves, how does f change in response to a change in t? Well, if x and y are functions of t, then any change in t is going to affect these, right? Okay. And then the changes there are going to affect f. So the changes in t affect both x and y, and those in turn affect x, or excuse me, f. So to measure how f changes with respect to t, we have to consider how it's changing these components individually, and then how those components are changing our f. And that's what's going on here. We're asking, this is our question, how does f change in response to t? Okay. Well, first, we say, okay, well, if t is changing, then x is changing. So this is how x changes in response to t. And then we multiply that by how f is changing in response to x. So that's taking care of the first component as t changes. And then we do the same thing for y. We say, okay, how is y changing in response to t? And then we ask, okay, how is f changing in response to y? And then we add these two terms together, and we should get our total change in f in response to t. Okay. We have a little proof, and I kind of abridged this bit. You can check the book for kind of a more wordy explanation. I'm going to talk my way through it. Okay, so we expect we're trying to find df dt. And really that's going to be what? The limit of delta f over delta t. And then, okay, we're kind of saying z equals fxy. So I'm just going to use the variable z in place of my f, as the book does. Okay. So I guess we should write dz over dt equals delta z over limit of delta z over delta t as t goes to 0. All right. And remember, this is just, well, I'll express, what is delta z? Okay. So remember, this is what we're looking for. Okay. What is delta z? Well, that's just the change in t. If I add an h, let's see. If I add a small h to that t, how does that change my z? Okay, so I'm adding h here. Okay, this is just like it's kind of parallel to our definition of the derivative for a single variable. Okay, so I'm adding a small h there, and then I'm subtracting just by my original. Okay, so this is my delta z. Now, from the previous section, since z, our function, is differentiable, and this is the multivariable definition of differentiable, we have this linear approximation, right? So remember what that linear approximation is. Okay, it's the partial f sub x times our change in x, our partial y times delta y, and then we have these error terms, right? Epsilon 1 times delta x plus epsilon 2 times delta y. And the limit of these go to 0 as delta x, delta y goes to 0. Okay. All right. But what's delta x? Okay, remember, delta x is a function of t. Okay, and it's differentiable. So by the same definition of differentiable, but for single variable, okay, we have this linear approximation for x. Delta x is going to be equal to what? X prime of t, the derivative of x, times our change in t, plus some error term, we'll call it eta 1 times delta t. And the limit of this goes to 0 as t goes to 0. And then we have the same thing for delta y. What is delta y? Well, since y is a differentiable function of t, we can write it like this. Okay. And this limit goes to 0 as delta t goes to 0. Okay, so now let's rewrite our delta z, and let's replace these. Oops. Let's replace these terms with, everywhere we see them, with these. Okay. Okay, so delta z is equal to this. I got my f sub x times delta, x prime delta t, eta 1 delta t, and so on. Then I have these error terms. And now notice that in this expression, I don't have any delta x's or delta y's. I just have my delta t's. So now basically what I have is this change in z, the change in my function, is written in terms of the partial derivatives and derivatives of x and y and delta t. There's no delta x's involved. Okay. And now, just simplifying, okay. Okay, so this is my delta z. Now consider delta z over delta t, okay. So all these delta t's are gonna get canceled out. I'm dividing by delta t, so these delta t's are gonna get canceled, right? Okay, and we have to, check and make sure that's that we've done that carefully and that works. That we can pull out a delta t from each of these terms and so on, and it works. You can check this. You can do the algebra on your own. Okay, even if you're having a little trouble understanding the concepts, you can follow through on the algebra of all this and do delta z over delta t and see what cancels. And you should see that once we do delta z over delta t, we end up with this. And again, okay, we have our delta z over delta t is written in terms of the partial derivatives of f, okay, the derivatives of x and y, and then these error terms, right? Eta 1, eta 2, epsilon 1, epsilon 2, okay? And we know in some sense these error terms are going to go to 0, right? As what? These are going to go to 0 as delta t approaches 0, right? Because they're coming from the derivatives of x and y. Okay. And then these are going to 0 as x and y go to 0. All right, now let's look at these. Okay. So, and let's think about this piece by piece. Okay, so consider, you know, we're ready to start considering the limit of all this, right? We have delta z over delta t. Let's start considering the limit of delta z over delta t, okay, as t goes to 0. Okay, first look at these two terms. Okay, I have my fx, my f sub x, and my f sub y multiplied by the derivatives of x and y respectively. Okay, so and then I have these parentheses here. So if I distributed this, what's going to happen? I'm going to multiply this here and this here. Okay. Well, when I take the limit of this term, this multiplication, I just get fx times x prime of t, right? And then when I take the limit of this thing, of this multiplication, well, the limit of this is 0 as t goes to 0, so that limit should go to 0. Okay. So the limit of that first line is just this. And then same thing with the second line. The limit of this goes to 0 as delta t goes to 0. So the limit of that line equals this. Okay. All right, now let's consider these two lines. Now the problem is the limit of epsilon 1 and epsilon 2, those limits go to 0 as x and y go to 0. Okay, so but we're considering the limit as t goes to 0. So there's a little hiccup there. But think about this. We know that the limit of epsilon 1 as x goes to 0 is 0. Okay. Let's see. But we said our function of x, or our x is a function of t, and that function is differentiable, right? So by our definition of differentiable, if t goes to 0, that implies x goes to 0. Okay. Why? Because I mean, it's not that x goes to 0. It's, let's see how to explain this. Oh, yeah, here we go. Oh, yeah. So the definition, it's not, this doesn't go to 0 as x goes to 0, it goes to x as delta x goes to 0, right? Okay. But x is a so x is a differentiable function of t, right? So it's also a continuous function of t. Okay, that's true for single variable functions. So since x is a continuous function of t, okay, delta t goes to 0 implies delta x goes to 0. Okay. So this limit, okay, it's originally written as delta x, and this should be 0. Okay, the limit of epsilon 1 is delta x goes to 0 is 0. But remember, if delta t goes to 0, then delta x goes to 0. So we could rewrite this as delta t goes to 0 as well. Okay. It's a little unrigorous, but it works. Okay. So the limit of this multiplication goes to 0 as delta t goes to 0. And, well, the limit of this goes to 0 as delta t goes to 0, right? So this whole term is going to go to 0. And then same thing with this one from the same argument. Okay. So the limit of this thing, which is going to be our dz dt, ends up just being what? This stuff we had from the first line plus this stuff we had from the second line. Okay. And that's just the norm, what you would expect from the chain rule. Okay. Forget about all the limits and stuff, and forget about our little proof. What would you expect dz dt to be? It's using chain rule. Okay, remember z is equal to f x of t, y of t. You'd kind of expect it that, okay, this derivative is going to be partial of x times derivative of x with respect to t, partial y times derivative of y with respect to t. Okay, and written in this nice, kind of compact differential notation, we have dz dt equals df over dx times dx dt, and actually this is not df, this is dou f dou x, right? Partial. So dou f dou x times dx dt. Okay, so now this is dx dt. Plus dou f over dou y times dy over dt. Okay, so let's explain this notation a little bit. Why am I using dou's here and d's here? Well, remember, f is a function of x and y, right? Okay, so it's got partial derivatives. Okay, so these need to be dou's, partials. Okay. And then x is a function of a single variable. So remember, for single variables, we use d's. Okay. So this is, somewhere you could lose just some minor notation points on a test. You have to keep your dou's and your d's straight. Okay. So if you didn't follow any of that argument or that little proof, don't worry about it too much. I would try and understand it, and if you need to watch that section a couple times and maybe check the book for a more kind of wordy example or wordy argument, check the book. But if that's not up your alley, just keep this formula in mind. Okay, we're going to see a couple of formulas. All right, so this is when, remember, we had fxy, kind of a function of two variables, and then each of those variables was a function of t. Okay, so that's our case one, so to speak. Okay, so let's try a problem. Okay, let's try actually applying this chain rule. All right, so our function of x and y, fxy, is equal to 2x squared plus 3y to the fourth. And then we're saying x, well, x is a function, is the function e to the power t, and y is equal to t cubed. So let's try and find df dt. Okay, so now let's look at our formula. Okay, and remember, we could just write z instead of f. And that's what the book does throughout the section. We could write df dt, but the book for whatever reason, prefers dz dt. Okay. All right. So to find df dt. Okay. So what is my formula for df dt? Or dz dt? First, partial dou f over dou x times dx dt. All right. Well, first step, let's look at our f and find our dou f or over dou x. Okay. So let's just write our formula again here. And I'm sure this, if you were looking at this and were confused, you know, I mixed my f's and z's. It should be like that. Okay. All right, so let's rewrite our formula and then just put our terms. I'm still doing it. Okay, that should finally be right. Okay. All right, and then let's find each of these terms one by one. Okay, what's this? Okay, to find that, I look at my function, fxy. Okay, and what's the partial with respect to x? Let's see, that would be 4x, right? All right, what's dx dt? Well, to find that, I look at this. What's dx dt? Well, that would just be e to the t. All right. Now, what's dou z over dou y? Again, I look at my original function. And what is it? So what's the partial with respect to y? 12y cubed. Yeah. And then what's dy dt? Look here. Okay. All right, so maybe I get that. And then the last thing, okay, I want it all in terms of t, okay? So what is x? I should rewrite x as e to the t. Okay. Similarly, I should rewrite y as what? T cubed. So I have y cubed, so I have t cubed cubed times t cubed. Simplify. Okay. So that should be my partial of, or excuse me, that should be my derivative of f with respect to t. Now, you might be asking yourself, and I seem to have a memory of asking myself this when I was in this class, like, why are we concerned with this case where, okay, we have fxy, and then it seems like kind of a pretty specific case when we're saying, all right, well, we're going to say x is a function of t and y is a function of t. Like, how often do you come across that? You know, it seems like it would be very niche. Okay. But don't be too restrictive in how you think about this. Don't think that this is only applicable when we have this very explicit x equals function of t, etc. Okay, so for example, let's say fxy is equal to this function here. Okay, and I want to find df dx, partial of f with respect to x, of this. Okay, so I've replaced, notice that I've replaced x with x squared plus 1 here. Okay, so this is like chain rule, right? This is kind of like chain rule for that we're used to. Like, how did chain rule pop up in Calc 1 and 2? You know, I had, maybe I had x squared plus 1 squared. And you say to yourself, well, if I just had x squared, the derivative of that would be 2x, right? And then, okay, so how does chain rule help? I still use the power rule here. I bring the 2 out front. I have x squared plus 1, and then I multiply by the derivative of what's inside, right? That's my chain rule for single variable. And the same thing's going on here, just with partial derivatives. You know, if I just had x, okay, that'd be simple. But I have x squared plus 1 in there, okay? So there's a couple ways to think about this. The way, you know, we can avoid chain rule if we wanted. One way to think about it would be like this, okay? Essentially what we're doing is, instead of plugging x into our function, we're plugging x squared plus 1 into our function, right? So if I could go back up to my original function and just replace all the x's with x squared plus 1, okay, which is what I've done here. And then you could just take the partial with respect to x of this thing, okay? So what would that give us? Okay, treating y like a constant, we would have 2x times y plus 2x ln y cosine x squared plus 1, and we're using a little single variable chain rule right here on the sine squared, or excuse me, the sine of x squared plus 1. Okay, so we would arrive at this. All right, that's all well and good, but this can be kind of complicated if this function f is complicated, right? What did we do? We had to go in and replace our x with x squared plus 1, and you know, if this thing's kind of complicated, that process can be a little nasty. Okay, so how can we use our chain rule theorem? Okay, so recall we had what? This. All right, so think of this as your x and y, just like it's stated. And then we're saying, okay, what's f x squared plus 1 y? Okay. Now think of this x as your t. So it's like what you're saying is, and maybe it would be simpler if we kind of did it like this. Think of this x as think of it as a very, you know, let's kind of rebrand it in our brains. Let's call them a and b. Okay. Well, then a is this function x squared plus 1, right? So it's like a of x. So same thing as a function of t, it's just we're using x instead of t. And then really we don't even have to do anything here. We could just do this. Okay. All right. So what would our chain rule tell us? Well, I should do, okay, if I wanted to find df dx, okay, that's what? Partial f with respect to a times derivative of a with respect to x. Okay, and then there's no x's in here, right? So this term's going to be 0. Okay, what is this? Okay, that would just be y plus ln y cosine x squared plus 1. And then what is this term? Well, that would just be 2x. And then if we multiply these out, we see we get the exact same thing as up here. Okay. So again, we didn't have any kind of explicit statement that, okay, x is a function of t, but we could still apply our chain rule. Okay. So really, if, you know, this, forget about my rambling explanation of how this worked. If you see something like this, maybe your intuition from Calc 1 and Calc 2 should tell you that, okay, this looks like a chain rule type situation. And then just remember the formula for chain rule. Okay. Now, we can make things even more complicated, and we're going to do that by assuming that f is a function of more than 2 variables. So let's assume it's a function of n variables. And then let's further suppose that each of these components, xi, x1, x2, x3, and so on, let's assume each of those is a function of r variables. So now, okay, we have multiple variables here, and then each of these is also a function of multiple variables. So x is a function of t1 to tr. So, so are all the other x's. Okay. Can we still use chain rule? Okay, yeah, we can. So what is df? What is df over dt1? And actually, these should be partials now. So we want to consider how f is changing in response to t1. But remember, as t1 changes, that's affecting all of these variables. Okay, so just like with the case 1 of our chain rule, okay, our total change in f should be the sum of the change in f with respect to variable x1 times the change in x1 with respect to variable t1, change in f with respect to x2 times change in x2 with respect to t1, and so on. Okay. So it's just adding more terms to our chain rule, really. So here's an example from the book. Okay. So take a second to digest that, and again, these should be partials. Okay. So now everything's partial, right? Because, okay, what I have is I have fx1, x2, x3, x4, and so on. Okay. If each of those x1, each of those xi's, if each of those was just a function of a single variable, then I could consider f as a function of a single variable, right? So I'd have df dt. Okay, if each x1 was a function of t, okay, if x1 was x1t and x2 was a function of t, and so on, then really I could consider x as a function of a single variable. So its derivative would be df over dt. Okay, but now what am I considering? Okay, f is a function of several variables, and each of those variables is a function of several variables. So I have x1 of t1 to tr, and so on to xn t1 tr. Okay. So now I have to at least consider f as a function of these r variables here. Okay. So now I have partials. All right. So let's assume we have a function of 3 variables, u of x, y, and z. And it's given by this equation here, which I just erased. Okay. And then what do we have? X is this function of r, s, and t. And y is this function, z is this function. Okay. Let's find du ds. When r equals 2, s equals 1, and t equals 0. Okay, so we're going to plug specific values in, but first we need to find just the general form of dou u over dou s. So what is that going to be? From my formula, I know that dou u over dou s should be what? Dou u over dou x times dou x over dou 1, dou s, plus dou u over dou y times dou y over dou s, plus dou u over dou z times dou z over dou s. Okay. So now let's just fill in each of these terms. Okay, so what's dou u over dou x? Okay, to find that, I go up to my original function. So what's the partial with respect to x there? Let's see, that would be 4x cubed times y. Yeah, just 4x cubed times y. Okay, what's dou x dou s? To find that, I look at this. Okay, so partial of x with respect to s. Well, that would just be r e to the t. Okay. Continuing my process, dou u over dou y. Oh, that'd be x to the fourth plus 2yz cubed. Well, it's dou y over dou s. Okay, so now I look here. See, that'd be 2 rs e to the negative t. All right, now it's dou u dou z. Let's see, that would be 3y squared z squared. Partial z with respect to partial z over dou z over dou s. Okay. So I look at this, that would be r squared. All right. So this is my dou u over dou s. Okay. And now, to be completely clear, I should probably replace my x's and y's with my functions here. Okay. I don't want any x, y's, or z's to appear in this partial, right? I want it all to be in terms of these things. A little terminology here, kind of the bottom level of variables, this stuff. These we would call the r, the s, and t, kind of in the most, the bottom level, that base level. We would call those the independent variables. And then these x, y's, and z's, which are kind of in the middle, we call those intermediate variables. Did I say random variable a second ago? That's from probability. So again, we call r, s, and t independent variables, and we call x, y, and z intermediate variables. Okay. So I don't want, when I write dou u over dou s, I don't want any of these intermediate variables, x, y, and z in there. I want it all in terms of the independent variables. So let's see. What's x cubed? Well, that would be this cubed. Okay. And I could rewrite all that. You know, if I was asking you to do this on a test, yeah, maybe you would have to rewrite that. Okay. What is this problem asking for, though? It's asking for dou u over dou s when we have r is equal to t, s is equal to 1, t is equal to 0. So there is a shortcut we can take to avoid doing all that conversion. Okay. What is the shortcut? Okay. What is x when I have r is equal to t, s is equal to 1, t is equal to 0? Excuse me, when r is equal to 2, s is equal to 1, t is equal to 0. What is x? Well, x will be, let's see, 2 times 1 times e to the 0, which is 1. Okay, so x of 2, 1, 0 is equal to 2. What is y of 2, 1, 0? Okay. Y of 2, 1, 0, it would be 2 times 1 times 1 over e. So 2 over e. What is z of 2, 1, 0? Oh, wait, no, it's just 2, right? Yeah, because let's see, y would be 2 times 1 times e to the negative 0, which is still just 1. Okay. All right, what is z of 210? That would be what? 4. So now let's plug these values for in for our x, y's, and z's, and then let's plug these values in for our s and t's. Okay. So my dou u over dou s at 2, 1, 0 be equal to what? Okay. 4x cubed, well, what is x? X is 2, so 4 times 8 times y, which is 2, okay, times r e to the t. What's my r? 2. What's my e to the t? E to the 0, which is 1. Okay. Plus x to the 4th. Okay, what's my x to the 4th? That would be 16. What's my 2yz cubed? That'd be plus 2 times 2 times 64. Okay. Oh, and then I need to multiply by what? 2rs e to the negative t. So 2 times 1 times e to the 0, which is 1. Okay. Plus what? 3y squared. Okay, so 3 times 4 times 16 times r squared, which is 4. And then we simplify this. I'm not going to bother adding all this up. This should give us our final answer. And this is an example from the book, so you should be able to tell if I've done everything correctly if you want to go in and check that. Okay. Tree diagrams. Tree diagrams can be very helpful in keeping track of everything. It's not something you have to do. I don't envision myself ever asking you for tree diagrams on a test. Maybe on the WebAssign, you'll have to kind of fill in some blanks or something like that. But they can be very helpful and help you keep track of things. So how can we use them? Okay. So let's start with a case. Let's start with this kind of general multivariable case. Let's assume I have f of x1 to xn, and then each of these x's is a function of t. Okay, just a single variable t. Okay, let's find a way to keep track of our chain rule. Okay, our derivatives. Okay, so I can make this tree diagram, and let's talk about just drawing the diagram first, and then how to apply it. So let's start by drawing our function f at the top of this tree, and then branches going down to each of the variables x1, x2, and so on to xn. Okay, so that's the first step. Okay, and then think of these lines as partial derivatives with respect of f with respect to that variable. Okay, so this line would be dou f over dou x1. Okay, and then this line would be dou f over dou x2, and so on. Okay. All right. And now what are we going to do? We're going to draw lines from x1 to t, because x1 is a function of t, right? Same thing with x2 and so on. Okay, so we have this, right? Another level of our tree. And then again, think of these lines as derivatives. So what would this first blue line be? That's dx1 over dt. And then this would be dx2 over dt. Okay. And let's see, let's kind of have all our derivatives in there. So this line again is dou f over dou x1, and then dx1 over dt. Okay. All right, so this is our, and this, now we're done drawing our tree diagram. And you don't have to label this as long as you you don't have to label these derivatives. Okay, as long as you can keep track in your head what they are, and you should be able to tell just by looking at it. Okay, I have f on this end, x1 here, so that line should be dou f over dou x1. Okay. Now, how can I use this tree diagram to find df dt? Okay. Well, to find df dt, you just add up all the paths from f to t. Okay. So what do I mean by a path from f to t? Okay. Well, this path here, this first path. Okay. What is that path? I would call that path d, or dou f over dou x1 times dou x1 over dt. Okay, so that's that first path. Okay, so I'm going to write that here. Okay, so that's my first path to t, and then I'm going to add up all the other paths to t. So what's this path to t? Well, that would be dou f over dou x2 times dou x2 over dt. Okay, so I'm going to put that second path in there. And then the third path and fourth path and so on, all the way up to n. Okay, and then I just add those up, and that is my df dt. Now, we can also use these tree diagrams to do the more complicated cases when we have we can use these tree diagrams to do the cases when we have f x1 to xn, and each of those x and xi's, whatever you want to call them, those are functions of several variables. Okay. The only thing we do is we add more branches on the bottom level. Okay. So let's look at the specific example. Let's say I have fx1 to xn, and each of those xi's is a function of s and t. Okay. And remember what we're assuming here. We're assuming f is a differentiable function of those variables, those intermediate variables, and then each xi is differentiable function of those independent variables. Okay. What would our tree diagram look like? Again, I start out the same way. I have my f at my top, and then I draw my branches to the x1s, x2s, all the way to xn. And then I have branches, let's see, each of these xi's is a function of s and t. So I have two branches coming out of each of my xi's going to s and t. Okay, so my tree now looks like this. And again, each line kind of represents a derivative, right? So now what if I want to find dou f over dou s? Well, I sum up all the paths from f to an s. Okay, so what's my first path to s? Okay, let's use yellow. Okay. My first path to s would be what, this, right? Okay, so what is that path? It would be dou f over dou x1 times dou x1 over dou s. Okay. So I'm going to put that here. What's my next path to s? Well, let's see, it would be this. Okay. Okay, so that path is what? Dou f over dou x2 times dou x2 over dou s. Okay, so put that there. And then I just add all those up. And I should get my partial derivative dou f over dou s. Okay. So really these trees are just a way to keep track visually of what partials you need to take, okay, and what chain rule you need to apply. Implicit function, the last section of our last topic in this section is implicit function theorem. It doesn't look like it comes up in the WebAssign, and it is important, but I think we can just talk about it briefly.